Hello children and welcome to my channel Chemistry by Miss Nidhi Banga. Today's topic of discussion is chapter 3 of grade 10, metals and nonmetals. So let's get started. In this video, I intend to walk you through the entire chapter, all the theory, all the important activities and all the important questions. So I'm beginning with metals and nonmetals. What are they? Their properties and most importantly, their exceptions. Okay, so metals, the metals that you're familiar with, iron, copper, silver, gold. But apart from that, we have zinc, sodium, potassium, magnesium, and calcium. They're all metals. They're found on the left side of the periodic table. Okay, non-metals, carbon, nitrogen, oxygen, chlorine, iodine. They are all non-metals. All right. Now let's talk about their properties. Metals are lustrous. That means they have a metallic shine on them. Now you have seen that metals like silver and gold, they are lustrous. But what about magnesium and zinc? They are also lustrous, but more often than not, they are covered with some oxide layer on top of them, which makes them look dull. Okay, but that is the oxide layer on it, not the metal itself. So if you remove it by sandpaper, you would see the metal beneath, which would be obviously lustrous. So all metals are lustrous. That means all of them have the metallic shine. Okay, non-metals are non-lustrous, except, there is an exception here, except iodine. Iodine is non-lustrous. And graphite. What is graphite? Graphite is an allotrope of carbon, which we know is a non-metal, right? So graphite is a lustrous non-metal. Some people write diamond also. I would beg to differ here. The thing is, diamond has shine, but it's not metallic luster. It's the crystal luster that it has. Okay, so I won't count diamond as a lustrous non-metal. Coming on to the next part, state. Metals are all solids except mercury. Mercury at room temperature is a liquid. Okay. Non-metals, they are solids, liquids and gases. Okay. Most of them are solids and gases. Bromine is the only liquid non-metal. It's not an exception. It's just a information. Bromine is the only liquid non-metal. Rest of the non-metals are all solid and gases. Okay. Hardness. Metals are hard. Metals are hard except lithium, sodium, potassium. They are all very soft metals. So soft that they can be cut with knife. Can be cut with a knife. Okay. Non-metals are not soft, are not hard. They are brittle. Not hard. Except diamond. Diamond, which is again an allotrope of carbon, is the hardest known material. So that would be an obvious exception. Next up, we have malleability and ductility. Their definitions are also asked. Malleability is the ability of a metal to be hammered into sheets. And we know that metals are malleable because we have seen aluminium foil, we have seen tin sheets, we have seen iron sheets, we have seen even silver sheets that we use on mithais, silver work. So metals are malleable. Ductility is the ability of a metal to be drawn into wires. We know that as well. Many jewelries are made because the metals can be drawn into wires. So silver and gold and copper, they all can be made into wires. So metals are malleable and ductiles. Non-metals are non-malleable, non-ductile. Okay, no exception here. All right. Next up, we have a property of metals, which is conduction of heat. Here we are talking about activity 3.5, where we have a metal wire screwed to a stand, and then on this end, on far end of the metal wire, we have sort of stuck a pin using a wax. Okay, using wax, we have sort of pasted a pin onto it. Okay, and then we are heating the other end of the wire. Now, we are heating this end, but after some time what we would see is that the pin drops, pin falls off. Why does that happen? Because this metal wire is a good conductor of heat. Even if you are heating this end, the heat travels to this far end, and from here it travels to the wax, which melts, and therefore the pin falls. Okay, so this activity proves that metals are good conductors of heat. This activity also proves that metals have a very high melting point. That is why the wire would not melt. Okay, so good conductors of heat. All metals are good conductors of heat except lead and mercury. Okay, they're not that great in conducting heat. Non-metals are poor conductor of heat. They are poor conductor of heat. Now, a question which is very commonly asked based on this activity is that why cooking vessels are made up of metals? Cooking vessels are made up of metals because of two reasons. First is that they are good conductors of heat. You would want the heat to go from your burner to the vessel and therefore to the food. Okay, so the vessel needs to conduct heat. Second thing is they have high melting point. You would not want your your cooking vessel to get melted while cooking. So it has to have a high melting point as well. Okay, so the next property is conduction of electricity. So here we are talking about activity 3.6. We have a basic setup, basic circuit, which has one battery, a bulb, a switch, and clips. If we put a metal here between the clips, the bulb will glow. Why? Because the circuit is complete. How? Because the metal will allow the electricity to pass through, proving that metals are good conductors of electricity. Metals are good conductors of electricity. Okay, but if we put a non-metal between these clips, the bulb will not glow in that case because the non-metal would not allow the electricity to pass. Okay, so the circuit would be as good as broken because the electricity is not being able to pass. In that case, the bulb will not glow. Okay, so non-metals are bad conductors of electricity. Non-metals are poor conductors of electricity. Except graphite. Graphite, which is an allotrope of carbon, is a good conductor of electricity. Why is that? This is graphite's structure. In that, we can see that each carbon is bonded to 3 other carbons. But carbon, as we know, has the valency of 4. So that means it has 4 valence electrons in its outermost shell, out of which it's using only 3 for bonding. Each carbon is left with 1 electron which is not being used for bonding. Hence, this electron is free for movement. And when electrons move, that will conduct electricity. Okay, so that makes graphite a good conductor of electricity. Okay, next up we have few more properties. Melting point. We know that metals have high melting point. Okay, except cesium and gallium. These two metals have melting point very low, just a little over room temperature. So if you keep these metals in your palm, they will melt. In fact, gallium used to be used in magic spoon trick. Okay, Google it. Non-metals have low melting point, except diamond. Okay, talking about density, metals have high density. Density, if you don't remember, it's mass by volume. Okay, they have high density. That means they have high mass per unit volume, except lithium, sodium, potassium. They're not very dense. Okay, they're very light metals. They're also very soft metals which can be cut with knives. Okay. Non-metals, they have low densities. Okay. Now, some questions, if questions are directly asked from the exceptions and properties, so I hope you'll be able to answer. But then there are some questions which are not directly taken here. Let's see. Non-metals other than carbon which are known to show allotropy. It's phosphorus. Allotropes of carbon are graphite, diamond, and Buckminster fullerene. Allotropes of phosphorus are red, white, and even black. Okay, these are the three kind of phosphorus. They have different structures, as in bonding is different, but the element is very much phosphorus. Next, non-metal other than carbon known to show catenation. This you will take up in chapter 4 as well. Catenation is property to link with itself. Carbon has that property, but apart from carbon, to a limited extent, silicon and sulfur also show this property. Okay, and they are also both non-metals. Non-metal required for combustion. Now this one is easy. For combustion, we have to have oxygen apart from the combustible substance. Okay, so oxygen is the non-metal which is required for combustion. No oxygen, no combustion. Okay, next up, chemical properties of metals. So we have certain metals, we will discuss their chemical properties. We will basically try to arrange them in the order of reactivity, going from least reactive to most reactive. But in order to do so, we need to check some of their properties. We need to see how they react with oxygen, that is how they react with air, then how they react with water, how they react with acids, and how they react with solutions of each other. Hopefully, after seeing how they react with all these, we will be able to arrange them in a certain order of reactivity. Okay, so these are the metals we will be talking about. But before we get to that, let's talk about an activity 3.8. Here, magnesium ribbon is burnt in oxygen or burnt in air, and sulfur powder is burnt in air. So magnesium ribbon, when is burnt in air, the product you already know. It's the, I think, second activity in the first chapter or the first activity. So here, when magnesium is burnt with air, we get a white powder, magnesium oxide. Okay, here we get a gas which gives the smell of burning sulfur. Okay, this white powder, when collected and then dissolved in water, it gives magnesium hydroxide. Sulfur dioxide, when dissolved in water, gives sulfurous acid. Okay, now I hope you can tell what would be the action of litmus paper on these solutions. Litmus paper, upon putting it in the solution of magnesium hydroxide, would turn blue. Okay, because this is a base, because metal oxides are basic. Whereas litmus paper, when put in this solution, would turn red, because this is an aqueous solution of a non-metal oxide. Non-metal oxide are basic. Okay, so let me just write here. Metal oxides are basic and non-metal oxides are acidic. Okay, these are the observations of this activity. Okay, now coming on to our agenda, main agenda, chemical properties of metals. Okay, now let's see how metals react with air. Metals react with oxygen in the air to form metal oxides. Okay, now let's see how different metals react with oxygen. Sodium and potassium, they react very vigorously. And hence they cannot be stored out in open air. They need to be kept. They are kept immersed in kerosene. That is how they are stored. Okay, we all know that magnesium burns with a white dazzling light, right? We saw that in the activity of first chapter. So we know that it burns with that and forms magnesium oxide, right? But also This happens when it's introduced in the flame. But even at room temperature, magnesium does react with oxygen to form magnesium oxide layer, which covers the metal. Okay, this oxide layer covers the metal and makes it unreactive to further oxidation. That is why before introducing into flame, we need to remove this oxide layer by using a sandpaper. Okay. Aluminium, zinc and lead, they also form an oxide layer, which renders them inactive. Copper does not react with oxygen at room temperature. Copper reacts with oxygen at high temperature upon heating only. Okay, when copper is heated, it forms copper oxide, which is black in color. I hope you remember this from chapter 1. This was the last activity of chapter 1. When copper was heated in air, it formed, the brown colored copper turned black because now it turned into copper oxide. Okay, then we also passed hydrogen gas over this black colored thing and it turned back to copper. That was the reduction part. Okay, now let's see about silver and gold. Silver and gold do not react with oxygen, even at high temperature. Okay, even at elevated temperature, they do not react with oxygen. And precisely that's why they are used in making jewelry. You would not want your jewelry to get tarnished upon reacting with oxygen. So gold and silver are very, very unreactive towards oxygen. That is why they are used in jewelry. Other reasons for them to be used in jewelry are like they are malleable, they are ductile, they have metallic luster. All these things, along with their ability to not react with oxygen, makes them ideal for making jewelry. Let's now talk about solubility of metal oxides. Metal oxides, some of them are soluble in water, like the most reactive ones, sodium, potassium, magnesium, and calcium. They would react with water, they would be dissolved in water, and they would be forming this, alkalis or hydroxides. Okay, let's balance it. Rest of them are balanced. So these are alkalis. Okay, so metal oxides, upon dissolving in water, they form alkalis, which proves the basic nature of metallic oxides or metal oxides. Okay, but these metals which are soluble in water and form alkalis, that's how they prove that these oxides are basic in nature. What about other oxides which are not soluble in water? How do we prove that they are also basic in nature? This is how we do that. Take the oxide, metal oxide, make it react with an acid. If it forms a salt and water, then that proves that the oxide being talked about is metallic. Why? Because the reaction that would be happening would be a neutralization reaction. HCl being an acid, if something that reacts with acid gives you salt and water, then that thing has to be a base. So since metal oxide react with acid to give salt and water, that proves that copper oxide, or this metal oxide in particular, is basic. Okay, let's see the salt that would be formed. Copper, the valency is +2. So upon reacting with the chloride part, the anion part of the acid, it would form cupric chloride and water. Okay, this is the salt and this is water. This is neutralization reaction. Now, we have seen that metal oxides are basic. Some of them dissolve in water and form alkalis, and all of them react with acid to form salt and water. But there are some oxides which are amphoteric. Amphoteric means they react with both acids and bases, okay, to form salt and water. There are two oxides in particular, aluminium oxide and zinc oxide. Aluminium oxide and zinc oxide are amphoteric oxides. So what happens is, aluminium oxide upon reaction with acid will form a salt and water. Okay, this proves that this is basic in nature. But when this also reacts with base to give salt and water, that proves that this is also acidic in nature. Now this is where the problem arises. Formula of the salt. There's a very simple way by which you can remember how to write the formula of the salt formed here, if you just pay attention to the equation. See, water is formed, so that means 2 hydrogens are needed. Here we have only 1 hydrogen. To balance, you put a 2 in front. Now what are we left with? We are left with 2 sodium, 2 aluminium, and 4 oxygen. Because see, 3 plus 2 more, that makes it 5. Out of 5, 1 is spoken for, so we are left with only 4 oxygens. Now we have to arrange these elements going from most metallic to least metallic. Out of sodium and aluminium, sodium is most metallic, aluminium is less metallic than that, and oxygen, as we all know, is a non-metal. Okay, now 2, 2, 4. If we do it like this, it settles the formula, right? So this is sodium aluminate. Okay, next up is the other amphoteric oxide, zinc oxide. When it reacts with HCl, it forms zinc chloride and water, proving that it's basic. It also reacts with NaOH to give a salt and water, proving that it's also acidic. Now, again, formula of this salt, let's figure it out. So, 2 hydrogen in water. Here we have just one, put a 2 in front. What are we left with? 2 sodium, 1 zinc, and 3 oxygens. 2 here, 1 here. But 1 is spoken for. So we are still left with 2 oxygen. 1 zinc, 2 sodium, and 2 oxygen. Okay, we will arrange these elements going from most metallic to least metallic. 2 sodium, 1 zinc, and 2 oxygen. Here you go. This is the formula of sodium zincate. Okay. All right. Now moving on to the next part. After seeing these reactions, the order that we came up with is sodium, potassium first, because we know that they react very vigorously. So they are obviously most metallic. Then we have magnesium. Then we have aluminium, zinc, lead, and iron. We could not find out which one is most metallic amongst these. Okay, so right now, after seeing the reaction with oxygen, for us, they all stand in one place. Then we have copper, which reacts with oxygen only upon heating, and then gold and silver, which don't react at all. So this is the order that we could find out after seeing their reaction with oxygen. So we need more information to arrange them in a proper order of reactivity. For that, we would now witness the next reaction of metals with water. So metals, upon reaction with water, they form metal oxide and hydrogen gas. This hydrogen gas makes bubbles, and we all know it can be detected because it makes a pop sound with a burning candle. Why? Because it's a fuel. Okay, so it forms a sort of chota sa blast which makes a pop sound. Okay, so let's see this reaction, this activity. We have here glass wool soaked in water. Then we have a metal here. This glass wool's purpose is to just hold the water. So when this part is being heated, the water in the glass wool will get evaporated and will travel here, and then it would react with the metal and will form metal oxide and hydrogen gas. Hydrogen gas would travel from here and it will form bubbles in water here. Okay, so this is the observation of the reaction. Let's see what happens next. Now we are talking about the observations of all the metals as they react with water. Potassium and sodium, yet again, they are very, very reactive. They react with cold water. Now the thing is, whenever we have to see whether something is reactive or not, or how reactive that thing is, what we observe is first how vigorous the reaction is. More vigorous the reaction, more reactive the metal is. Second thing, we also see how much temperature is needed to initiate the reaction. If the reaction takes place at cold temperature or room temperature, the metal is reactive. If it doesn't take place at cold temperature or room temperature and it needs higher temperature, then the metal is less reactive because it needs more energy to get the reaction started. Okay, so what we observed was that potassium and sodium, they react with cold water. Okay, that means they're very, very reactive. They can even react with cold water. And the reaction is very vigorous. And it catches fire. Why does it catch fire? We just saw that upon reaction, the general reaction that we saw was that when metal combines with oxygen, it forms oxide and hydrogen gas. Hydrogen gas is a fuel. And this reaction being vigorous, that means a lot of energy is released, a lot of heat is released. And that heat combined with the fuel makes it light. Okay, so it catches fire. Calcium also reacts with cold water, but the reaction is less vigorous. That means that calcium is not as reactive as potassium and sodium because the reaction is less vigorous. Since it's less vigorous, that means that less energy is produced. Since less energy is produced, it was not enough to light fire. So calcium does not catch fire. But what happens is the hydrogen gas that was released forms bubbles, and those bubbles stick to the surface of calcium, makes it lighter, and calcium starts floating. Something similar happens with magnesium, but it happens at a higher temperature. Magnesium reacts with water, but only upon heating. That makes magnesium less reactive than calcium. Okay, upon reaction, the same thing happens. Hydrogen bubbles are formed and they stick to the surface of magnesium metal, make it float. Next, we have aluminium, zinc, and iron. We still are not able to differentiate between these using reaction with water because they all react with steam. They are definitely less reactive than the metals we just discussed because they don't react with cold water or hot water. They react only with steam. That means they need much more energy to react with water. Okay, so they are definitely less reactive than the metals we just discussed: sodium, potassium, calcium, magnesium. Then lead, copper, silver, gold. They don't react with water at all, not even with steam. Now let's discuss the reactions. Sodium, when reacted with water, we saw that formed sodium oxide and hydrogen gas. But sodium oxide is soluble in water. So it's fine if you just write sodium plus water gives you NaOH and hydrogen gas. Okay, because as soon as Na2O is formed, it gets dissolved to form NaOH. Okay, same thing happens with potassium, calcium, and magnesium. They all form the oxides which are soluble in water, and hence they get converted into hydroxides immediately. But after that, it doesn't happen with aluminium, zinc, and iron. They react with water to form oxides which are not soluble in water. So you would have to write just the oxide. Okay, you will not write hydroxide. Similarly, iron, upon reaction with water, it forms Fe3O4 and hydrogen gas. I'm not balancing the reaction, but the thing to notice here is Fe3O4. What is Fe3O4? We know that iron has two valencies, Fe2 plus and Fe3 plus. This is a mixture of ferrous oxide and ferric oxide. That means iron 2 oxide and iron 3 oxide. So Fe3O4 is a mixture of both. Both oxides are formed. Hence the formula Fe3O4. Okay. And like I said, these two oxides are not soluble in water, so you cannot write hydroxide. Whereas sodium, potassium, calcium, magnesium, their oxides are formed, but they are soluble in water. So as soon as they are formed, they turn into hydroxides. Okay. Next up is reaction of metals with acids. Okay. So metals, upon reaction with dilute acids, they form salts and hydrogen gas. Okay. Hydrogen gas again makes a pop sound with burning candle. Let's take an example. Zinc plus HCl gives you zinc chloride plus hydrogen gas. Okay. Exception. Exception is that not all acids give hydrogen gas with metals. HNO3 does not liberate hydrogen gas. Doesn't liberate hydrogen gas upon reaction with metals. Why does that happen? That happens because HNO3 is a very good oxidizing agent. So it does react with metals to form hydrogen gas, but as soon as hydrogen gas is formed, it is converted, it is oxidized to water. And HNO3 itself gets reduced to lower oxides of nitrogen, like NO, NO2, NO3. Okay, so HNO3 does not liberate hydrogen upon reaction with metal. Why? Because as soon as hydrogen is released, HNO3, being a very good oxidizing agent, converts it into water, oxidizes hydrogen into water, and itself gets reduced to lower oxide. Okay. Now, there's an exception of the exception. With two metals, manganese and magnesium, very dilute manganese and magnesium, when react with very dilute HNO3, they do liberate hydrogen. Hydrogen is liberated when HNO3, very dilute HNO3 reacts with manganese or magnesium. Okay, so these two exceptions you have to remember. After that, we have magnesium, aluminium, zinc, and iron. They all react with acids and liberate hydrogen gas. So they all are sort of in one place. Sorry, not in one place. When they react with hydrogen, when they react with acid, they liberate hydrogen. But looking at the vigor of the reaction and how much heat was liberated and the speed at which bubbles were formed, we could deduce that magnesium is more reactive than aluminium, which is more reactive than zinc, which is more reactive than iron. Okay, so this we could deduce just by observing the reaction, observing the speed of the hydrogen bubbles and the heat liberated. Talking about the rest of the metals, they do not react with dilute HCl. Okay, so after seeing these reactions of metals with acid, we did get a very good idea of the reactivity of different metals, the order of reactivity of different metals, and we confirmed that with the reaction of metals with the solution of other metals. If you remember, this reaction, this type of reaction is called as displacement or single displacement. Here what happens is, if the metal, the solid metal, is more reactive than the metal salt here, then this metal would replace this metal from its salt. Okay, let's see with an example. If we take an iron nail and put it in the aqueous solution of copper sulfate, we would see that the solution starts turning green from blue. Copper sulfate is blue in color, right? From blue, the blue starts to fade and slowly it starts looking more of a green. Okay, because ferrous sulfate is green. And the iron nail starts to have a brown deposit on it. The iron nail starts to have a brown deposit on the outside. This brown deposit is nothing but copper. So, iron being more reactive than copper could displace copper from its salt solution. Okay, this is displacement. By this reaction, we can deduce that iron is more reactive than copper. Okay, this reaction does not happen. Copper, since it's less reactive than iron, is not able to displace iron from its salt solution. In these kind of reaction, you can always write the states. The metal would be solid and the salt solution, because it's a salt solution in water, we can write aqueous. Okay, now after all these reactions, we could deduce the reactivity order of metal, and it goes something like this: sodium, potassium, calcium, magnesium, aluminium, zinc, iron, lead, hydrogen, copper, mercury, silver, gold, platinum. Okay, and there's a mnemonic there which is quite catchy, and you can remember the mnemonic. Kabali ne car mangi, alto zen Ferrari, public hui curious, hangama aag or patake. Okay, this mnemonic helps me very much to remember the reactivity series. Okay, I hope it helps you too. Now we will see how metals react with non-metals. Metals, as we know, are the ones which have 1, 2, or 3 valence electrons in their outermost shell. Non-metals are the ones which have 5, 6, or 7 valence electrons in the outermost shell. Let's take examples. Sodium. Atomic number 11, 281 is the electronic configuration. Similarly, chlorine, atomic number 17, 287 is its electronic configuration. Now, as we can see that sodium has 1 valence electron and chlorine has 7 valence electrons. Sodium, if it wants to complete its octet, it can either gain 7 electrons, which is very, very energetically impossible, or it can just get rid of this electron. Okay, then its octet would be completed. Chlorine already has 7 electrons in its outermost shell. Now, it would be very difficult for it to remove all the 7. Rather, it would very easily gain 1 more electron and complete its octet. Okay, so what happens is sodium wants to sodium wants to lose an electron. Chlorine wants to gain an electron. So the transaction just happens. Sodium loses its one electron to chlorine. Okay, so metals, if we were to define metals, metals are the ones which have 1, 2 or 3 valence electrons in their outermost shell, and they tend to lose electrons and form cations. Non-metals, on the other hand, they have more number of valence electrons in their outermost shell, and they tend to gain electron and form anions. Okay, when cations and anions are formed, we know that they have opposite charge and therefore they will attract each other. Okay, and they will form a compound. Now let's see how to show the electron transfer in an electron dot structure. First of all, we would write the symbol of the element in center. Then we will show just the valence electrons. Just the valence electrons. Sodium has one valence electron, so we will show just one dot here. Chlorine has 7 valence electrons, so we will have to show 7 electrons. For that, we would use crosses. Okay, now we have shown 7 valence electrons of chlorine around its symbol. Next up, what we'll do is, we will show that the sodium is losing this electron to chlorine. In doing so, next you will show that sodium, since it has lost its electron, it has formed a positive charge. Chlorine, since it has gained one electron from sodium, it has gotten a negative charge. Okay, so this is the cation, this is the anion, and they will form compound together. Okay, so this is how we have to show the electron transfer. Things that we need to be careful about is, first, show only the valence electrons. Do not show the inner electrons. Okay, these are not to be shown. Then use different symbols for different elements. Different symbols of electron. Like for sodium, if you're using dot, for chlorine, use cross, or vice versa. Okay, but use different symbols for electron, for showing electron. Now let's see what happens when things get a little complicated. Let's talk about magnesium chloride. Magnesium, we know, is atomic number 12, 282. So we have to show 2 dots here, showing the valence electrons. Chlorine, as we know already, that it has 7 valence electrons. So we show 7 crosses. Now, chlorine, one atom of chlorine would be willing to accept just 1 electron from magnesium. It would not accept both because it needs only 8 electrons in its outermost shell. 7 it already has, it's short of just 1. So it would accept 1 electron from magnesium. Now, magnesium wants to lose both of its electrons. So 1 electron it will go to this chlorine, and the other electron it will give to the other chlorine atom. So here, like this, the transaction happens. Magnesium loses both its electrons, but to 2 chlorine atoms. So how would you show after that? Magnesium, since it has lost 2 electrons, you would not show any dots now. You will show 2 positive charge upon losing 2 electrons. And chlorine, you would show each chlorine with just 1 electron and 1 negative charge, but you would show 2 of them. Okay, this is how you show magnesium chloride. For magnesium oxide, very quickly, magnesium, 2 electrons, oxygen, atomic number 8, 2,8 is the configuration, 2,6 is the configuration. Oxygen is short of 2 electrons. Magnesium wants to lose 2 electrons. So magnesium would lose both its electrons to 1 oxygen atom only. Upon doing so, magnesium gains a Mg2 plus charge. Oxygen, since it has gained 2 electrons from magnesium, it gains a 2 negative charge. Now, 2 positive here, 2 negative here, you have to take the lowest ratio possible. So the formula would become MgO, because the lowest ratio would be 1 magnesium, 1 oxygen. Okay. Now that we have seen the formation of ionic compound, let's now study their properties. Activity 3.13, it talks about 3 ionic compound, sodium chloride, potassium chloride, and barium chloride. We introduce these compounds into the flame and we observe the flame color. So what we observe is that sodium chloride gives a yellow, orange or orangish yellow, whatever, yellow-orange flame. Potassium chloride gives a lilac-colored flame. Barium chloride gives an apple green color or grass green color. Apple green or grass green color flame. Okay, these are distinct color. They can be used for identification of salts. That means if you don't know which salt is this, it could be like sodium chloride or potassium or barium, all three of them are white in color. You can know which one is it by introducing them into the flame. The color of the flame will tell you the identity of the salt. The activity also talks about the solubility of these salts in water and kerosene. So, ionic compounds, all ionic compounds, the ones which are formed with ions, they are all soluble in water. Why? Ionic compounds have ions, positive and negative. Water is a polar compound. That means it also has positive and negative end. Okay, so water being a polar compound dissolves ionic compounds. Okay, whereas kerosene and oil, kerosene or petrol, they are non-polar. Non-polar means they won't be able to dissolve ionic compounds. They would be able to dissolve covalent compounds or non-ionic compounds. State, ionic compounds are all solid. Why they are solid? Because there's a strong interionic attraction. Okay, strong interionic attraction means strong attraction between cations and anions, which keeps them very close together. Therefore, they resemble the state of a solid. Okay, where particles are very close together. Boiling point and melting point and boiling point, they have very high melting point as well. Again, a reflection of strong interionic attraction. Conduction of electricity. Ionic compounds do conduct electricity, but not in solid state, only in molten or aqueous state. Why molten or aqueous state? Now, to be able to conduct electricity, there has to be a movement of charges. When ionic compound is in solid form, the ions are very strongly pulled towards each other, towards the opposite ion. Okay, and those strong interionic forces are keeping these ions in their place, not allowing them to move. But when we give enough heat, what happens is cation and anions are pulled apart. When we give enough heat equivalent to their melting point, the cation and anion are pulled apart and they are now not as much attracted towards each other because the distance has increased and therefore they can travel. They are free to move. Since they are charges which are able to move, they conduct electricity. Same happens when they are dissolved in water. That means in the aqueous state. In aqueous state also, the cation and anion separate and therefore they are able to move. So conduction of electricity happens for ionic compound, but only in aqueous or molten state. Next, we would be talking about metallurgy. Metallurgy is the extraction of metals, right? Now, this topic will take very quickly. First is minerals and ores. Minerals are the elements or compounds which occur naturally in Earth's crust. Okay, they can be elements or the compound of elements which occur naturally in Earth's crust. When a mineral is called an ore, a mineral is called an ore if the concentration of the element or compound of interest is high enough for us to extract it profitably. There has to be profit in extraction. If the mineral contains very little compound or metal, then the cost of extraction might exceed the profit we get from the metal or the compound, right? So it's important that the mineral from which we are extracting the metal or its compound has to have enough concentration of the metal or its compound. So mineral from which the metal can be extracted profitably, economically, that mineral is called as an ore. Okay. Now, ore doesn't just have mineral, it also has earthy impurities. Okay, that means sand, mud, leaves, small pebbles, rocks. They are collectively called as gangue. Now, this gangue has to be removed first before going further with the extraction process. And this removal of gangue is called as enrichment of ore. So the ore has to be enriched, meaning the gangue has to be removed before going further with the extraction processes. Now, extraction processes differ depending upon the metals which are being extracted. Highly reactive metals are never found in free state because they are highly reactive. They would react with whatever is nearby. So they are always found in compound state. Always found as compounds. And they are best extracted using electrolysis. This process I have already discussed in one of my videos. The name of the video is electrolysis, which has electrolysis from this chapter and from previous chapters in a compared basis. Okay, so do watch it if you want to review the electrolysis. Then comes moderately reactive metals, zinc, iron, lead. They are found as sulfides, oxides, or carbonates. To extract them, first of all, we have to convert them into oxides. If they're already in oxides, already in the form of oxide, good. If not, they need to be converted to oxide. Why do we need to do that? Because oxides can then be easily reduced. Oxides can then be easily reduced to get the metal. When we talk about low reactivity metals, such as copper and mercury, they are usually found as sulfides. Even silver, if not found in free state, it's found as sulfide. They also need to be converted to oxide and then reduction happens. Gold, platinum, and silver, they are least reactive. They are mostly found in free state. Okay, so they all only need to be refined. Okay, before going further with the extraction methods, depending upon the reactivity of the metal, first let's discuss the method to convert different ores, different minerals into oxides. There are two ways of doing that. Roasting and calcination. The difference is very commonly asked in board exam. So let's pay attention. We can write four differences. First is roasting. Roasting is done for sulfide ores. How? If let's say we have zinc sulfide, we need to convert it into zinc oxide. Okay, so for that we need to give oxygen. Yeah, because zinc sulfide does not have any oxygen. So roasting is done when the mineral is heated in presence of oxygen. Oxygen here is important because in product we want oxygen. And zinc sulfide does not have any oxygen. So remember it like this way. So when the sulfides are heated in presence of oxygen, it gives us oxide and sulfur dioxide, which is our one of the differences. It's done for sulfide ores. It's heated in presence of air. The sulfide is heated in the presence of air and the byproduct is sulfur dioxide is liberated. Okay, and in the fourth difference, you can actually write the reaction. So, roasting is done for sulfide ores. It is done by heating the sulfide ore in presence of air. Second difference, sulfur dioxide is liberated. How do you know it's sulfur dioxide? Because it gives the smell of burning sulfur. Okay, and in the fourth difference, write the reaction. Calcination is done for carbonate ores. So when you have carbonate ore, you perform calcination or you convert it into oxide by simply heating it, not in the presence of air, in the absence of air. Why? We already have oxygen in the reactant. All we have to do is get rid of the extra carbon and extra oxygen. So just heat it and you would get zinc oxide and carbon dioxide. So calcination is done for carbonate ores to convert it into oxide by just heating the carbonate ore in absence of air. Okay, here carbon dioxide is liberated, which we can test by passing into lime water. It turns it milky. Last difference, you can write the reaction, this reaction. Let us talk about the reduction methods that are available. Once we have converted sulfides or carbonates into oxides, we have to reduce them. For reducing, we have three methods available. First, we can just heat them. This works well for low reactivity metals. Or we can use a reducing agent for middle order reactivity metals. Reducing agent that we often use is coke. Coke is nothing but carbon. Okay, it's derived from coal. It has high percentage of carbon, and carbon, as we all know, is a good reducing agent. When coke doesn't work, then we have to use reactive metals. Okay, so sodium, calcium, aluminium are often used as reducing agents because they tend to get oxidized, and in doing so, they reduce others. Therefore, metals are good reducing agents. Now let's see how we can extract metals of low reactivity. So in this we have two mainly, mercury and copper. Mercury's ore is called as cinnabar. This is also sometimes asked in MCQ. Cinnabar is the name of mercury ore, and that ore is nothing but mercury sulfide. So to convert it into oxide, we have to heat it in the presence of air. And I hope now you can tell this process is called as roasting. Once mercury oxide is created, then that can be reduced simply by heating. When we heat it, we get mercury and oxygen because this is a very weak bond, breaks only by heating. Then we have copper. In copper, what happens is, same, it has sulfide ore. It has to be heated in presence of air to give oxide. Then this oxide, which is now made, is made to react with the ore itself and heated. In doing so, it gives us copper and sulfur dioxide. Okay, this is how copper is extracted from its ore, which is a sulfide. Then this copper is later on refined. Now, moderately reactive metal, we have zinc sulfide, which can be then heated in presence of oxygen to give us zinc and sulfur dioxide. Zinc oxide, sorry. So zinc oxide is the oxide. If we have zinc as zinc carbonate, then we need to heat it in absence of air to give us zinc oxide and carbon dioxide. Okay, so once the oxides are formed, this oxide is then converted into or is reduced to zinc by using coke. It gives us carbon monoxide as a product. Okay. Talking about reduction when coke doesn't work. When coke doesn't work, we use reactive metals for reduction. Example of this reaction is when we have manganese oxide. We treat it with aluminium, which is a reactive metal. It will take oxygen, it will displace manganese, and oxygen would react with aluminium to form aluminium oxide, and manganese would be liberated. Okay, in this reaction, a large amount of heat is liberated. So much so that the manganese is produced in a liquid form, in a molten form. Okay, this reaction has special uses, especially when we use it with ferric oxide. When we take ferric oxide, mix it with aluminium solid, and make the reaction happen, because the reaction needs a little bit of heat. Okay, so when that little bit of heat is given, the reaction goes forward and iron is produced in liquid state because the reaction is so exothermic, and aluminium oxide is also produced. Now, the main use of this reaction is that we use it to repair cracks in railway tracks. So what happens is, we use this mixture, it's called as thermite mixture, because the reaction is called as thermite reaction, because it's an exothermic reaction, so therm comes from there. This mixture, thermite mixture, is made to fall in these cracks. Okay, and then the train is allowed to pass through it. With the friction, because of the friction created, the heat is liberated. And since heat is liberated, that heat is used to make the reaction go in forward direction, and iron is produced in liquid state, and that iron fills the crack. And this is how the railway tracks are repaired. Okay, all we have to do is put the thermite mixture, that means Fe2O3, that is ferric oxide, and aluminium in the cracks, and allow the trains to pass through it. From the heat liberated because of the friction, the reaction goes forward, iron is produced in molten state, which fills the crack, and repair happens. Next, let's talk about corrosion. What is corrosion? Corrosion is gradual deterioration of metal upon chemical or electrochemical interaction with its environment. Okay, we all know the best example of corrosion is rusting. So that is iron being deteriorated upon reaction with its environment. What is there in environment? We have air, which has oxygen, which has sulfur dioxide, which has H2S, which has carbon dioxide, and it also has water as moisture, right? So air has all these components, and these components do react with metal and deteriorate it over time. So this is an activity number 3.14, and let's see what happens in this activity. Here we have 3 test tubes. The first test tube has water and air and has a nail, iron nail in it. The second test tube has water, but it's not any water, it's boiled water. And then there's a layer of oil onto it, and then there's a iron nail which is completely immersed in the boiled water. Then in the third case, we have test tube, no water, only iron nail, and here we have anhydrous calcium chloride as well. Anhydrous calcium chloride is a good drying agent. So let's see what happens in each case. In the first test tube A, we have air, we have water. Okay, therefore rusting takes place. Iron gets rusted. Okay, in the second test tube, we have no air because the air could not dissolve because of the layer of the oil. And what about the air already dissolved in water? Oxygen is usually already dissolved in water. We call it dissolved oxygen. But this water is not any water, it's boiled water. So when this water was boiled, the dissolved gases, any dissolved gases would escape, because solubility of gases decreases at high temperature. So when we boil it, the solubility decreases, that means they all escape. So this boiled water does not have any dissolved oxygen, and more oxygen cannot be dissolved because there is a barrier of oil, right? So here rusting will not happen because there is no air, no rust. In this case, we have no water, of course. We have air, but air also usually has moisture. But then this is anhydrous calcium chloride, which is a good drying agent. That means whatever moisture was present in the air inside the test tube has been absorbed by anhydrous calcium chloride. So now this test tube does not have any moisture. It has oxygen, but it doesn't have any moisture. And we see that even this does not get rusted. What does this activity prove? This activity proves that in order for rusting to take place, or in order for corrosion to take place, oxygen, or in other words air, and water both are needed. Okay, in second test tube water was there but there was no air. In third test tube there is air but it's completely dry, there is no moisture. That is why in these two only one component was present, the other was not there, and therefore rusting could not take place. Now let's talk about rusting. Different kinds of rusting. Corrosion. Let's now talk about corrosion. Corrosion in silver is because of the silver sulfide that is formed. It forms a black colored layer onto silver and we call it tarnishing of silver. Tarnishing of silver is silver being corroded, and the formation of the compound is silver sulfide. We know that sulfur comes from air. Copper, when copper gets corroded, it forms basic calcium, basic carbonate of copper. Basic carbonate of copper. That means there is copper carbonate and then there is also copper hydroxide. Both of them are formed. This layer, this compound gives a green color layer onto the copper. Okay, this is the reason why Statue of Liberty looks green. Then we have iron. Iron, when gets rusted or when gets corroded, it forms iron oxide and hydrated iron oxide. But the amount of the amount of water molecules, it's not fixed. It varies. So we write X. So this iron oxide, this hydrated iron oxide is brown in color. We all know rust is brown in color. Okay. So these are the metals and this is how they rust and the compounds they form upon corrosion. Corrosion of iron is called as rusting. Corrosion of silver is called as tarnishing. Now, prevention of corrosion. Prevention of corrosion is a billion-dollar industry. It's very, very important that corrosion is prevented at all costs. Because you see dams, buildings, and all these structures that are made, they usually use iron to give it structural integrity, to give it some strength, right? Now, if iron in that gets corroded, gets rusted, it basically goes from being solid metal to being a powder. And imagine what will happen to the structural integrity of the building if the thing that was providing all the strength turns into a powder. Obviously, the building would collapse. And that would lead to huge loss of not just money, but lives. That is why it's very important that we prevent corrosion. Now, there are many ways to prevent corrosion, painting, oiling, but I'll be taking the more important two prevention methods. One is galvanization, the other one is alloying. Galvanization is when iron or steel is coated with a layer of zinc. When iron or steel is coated with a layer of zinc. Now, why only zinc? Zinc, if you remember the reactivity series, zinc is more reactive than iron. Then why are we treating iron with a more reactive metal? That is because zinc layer, when combines with oxygen, forms zinc oxide, which then combines with water to form zinc hydroxide, which then combines with carbon dioxide to form zinc carbonate. And this zinc carbonate layer adheres to the coating and forms a protective layer, which prevents even zinc from getting corroded. Okay, but that's not all. That's not why we use zinc. We use zinc mainly because even if the zinc coating is broken, iron would still not get rusted. That is because zinc is more reactive than iron. When zinc coating is broken, zinc and iron both are exposed to air. Now, zinc being more reactive will get preferentially corroded. And since zinc is getting corroded and not iron, iron is protected, therefore the structural integrity of the building is protected, right? So this is why we use galvanization. In galvanization, this is why we use zinc. Zinc, because it gets preferentially corroded, is called as sacrificial metal. Because it sacrifices itself for iron. Now that was galvanization. Next, let's talk about alloy, and that would be the last topic of today's class. An alloy is a homogeneous mixture of two or more metals or a metal and a non-metal. Different examples of alloys are 22 karat gold or less than that, like 16 karat, 18 karat. They are all alloys because pure gold is very, very soft. You cannot make jewelry out of it. So it has to be mixed with some other kind of metal. Usually they use copper and silver to give it some strength so that it can be molded into different shapes. Then we have steel. Steel is, gold is gold plus silver or iron or copper. Then steel is iron plus carbon. Carbon here is the non-metal. Okay. Then stainless steel is iron plus carbon plus nickel plus chromium. Amalgam is any alloy which has mercury in it. So a silver amalgam would have silver and mercury. If you know, silver amalgams are used as dental implants. brass, bronze, and solder. Now, brass and bronze, they are both copper alloys. Students usually remember this copper, but they don't remember the other component. They especially get confused because one has zinc and the other one has tin. So the way I remember it is brass has S sound. So apart from copper, it has zinc, which is Z. Bronze has Z. So apart from copper, it doesn't have zinc, it has tin, which starts with an S. So it's a cross connection sort of thing. That is how I remember. I hope it helps you too. Solder is lead and tin. You'll just have to remember, there's no other way. Then talking about the physical properties of alloys change. Hardness obviously increases because that is why we make alloys. Melting point decreases. Electrical conductivity also decreases. Apart from hardness, their tendency to get corroded also decreases. Tendency to get corroded decreases. So hardness increases, melting point electrical conductivity, and tendency to get corroded decreases. That is all about metals and non-metals. I hope this helped. And if you have any other topic you need help with, please let me know. And if you like the video, please subscribe, share, and like.